All right, gang. So, Joe Chemist, I hope you're all staying safe. I hope you're all productive, and I hope you're all making the best of this situation. Most importantly, I hope you're all healthy, you and your family and friends. For those celebrating Easter, happy Easter. For those in the middle of celebrating Passover, happy Passover. And anyone else celebrating anything, you know what? I hope it's going really well. So I just have a few things that I always have to write down because I always forget. Happy Easter, happy Passover, happy whatever. I want to give a big shout out to my mom, Norma Del Nano, the Facebook fiend. You can't hide anything from her on the Facebook. Mom, just want to say hi, happy Easter, and stay inside because I love you. And to anyone out there, make sure you call your grandparents because I bet they want to hear from you. Okay, a few things before we get started. I'm really happy with the review for today. I know I was supposed to have it last week, but I think delaying it a week really made it very, very, very quality. If you want a Joe Chem sticker, I've been sending letters like crazy. I've been sending letters to Louisiana. I've been sending letters to Tennessee. I've been sending letters to Texas. I have stamps. I have a pen. I'm feeling dangerous. If you want a sticker or even more to give to some friends and family, just let me know. That's why I bought them in the first place. They're 100% free. Otherwise, they're just sitting in a box in my room, right off camera. Anyways, gang, this is now the Joe Chem's been live for about 3.5 years now. I started off in an Ochem II semester in the spring 2017. This is now, end of spring 2020. I have about 96,000 views across all my videos. I can't believe that. I can't believe anyone's eyeballs are even on these videos. So I want to say thank you. In this year alone, there have been 45,000 video views. I was so stoked if I even got a few thousand in a semester. So I'm glad that you've been finding them helpful. I hope you've been finding them helpful. But I want to help others, so help me help them. If you subscribe, it allows me to do things on YouTube like go live on my phone, which I wish I could do YouTube live instead of Facebook live because, to be honest, the video quality is better. Subscribe, follow me on Instagram. Over the summer, I have so many plans. I'm going to get TikTok going, which, to be honest, I have some funny ideas. So I'll be making sure to advertise all of that, but tell your friends. Honestly, I'm a very bad marketer. You are unofficially my front lines on the marketing front. If you have friends taking Ochem, please tell them about Joe Chem, okay? I would so unbelievably appreciate it. Also, if you have 5 seconds, more like 2 minutes, please fill out the Google form on the website. It's linked on the homepage. It's whether you go to just joechem.io or joechem.io/free content home or joechem.io/home, whether you're signed in or not signed in or signed out. Give me some feedback. I'm so ready to make so many awesome changes to the site now that I'm finally almost done making content and catching up on that front. So let me know. Give me your thoughts. I've already got some great suggestions, so thank you for that who have filled out the Google form. And thank you for a great year. This has been so much fun. It's just, it's a thing I like to do in my spare time, and it's great that people are actually using it because it makes it worthwhile. So I just want to say thank you. But without further ado, let's do some chemistry, okay? So the way I kind of want to do this first, I want to start off in benzene land, do the second round of benzene chemistry. So I'm talking ipso substitution, talking nucleophilic aromatic substitution, doing some stuff with phenols. And then I want to work my way to carbohydrates. And then after carbohydrates, we can dip into heterocycles. And then we can round out the last live review of the semester of 2020, spring semester, with DNA, peptides, and amino acids. So let's get going. So this review is going to be very problem heavy. So it's going to, I'm not going to go into so much detail. If you want additional detail, please check out the corresponding videos on Joe Chem. I almost have all of heterocycles uploaded. I need to finish maybe a few extra videos. And I will be working on the DNA stuff literally as soon as I'm done with this live review. So let's get going. So right off the bat, I want to talk about do just a couple of problems. So if we were looking at something like this, I just want to throw up a couple problems and then we can kind of go into what kind of concepts this wraps in as far as so if we had something like this, you know what? It's definitely. Oh yeah, yep, that was right. Sorry, gang. Came in all hot, came in just a little. Can't read my own handwriting. Okay. And then one more. Okay, so I just want to start off with a few complete the reaction questions. And this is really going to focus around oxidation at the benzylic position, cleaving ethers at the benzylic position. Yeah, so if you can see in this first reaction up top, so in this second take of benzene chemistry, we have this formal introduction to oxidation at the benzylic position rather. The benzylic position being this carbon straight off the benzene ring, right? So a benzene ring, right, if you have a carbon right off of it, this we can refer to as the benzylic position. There's a whole bunch of resonance available at that position. We can do some magic at that position. So if you are to expose, some type of benzene derivative to manganese oxide only at the benzylic position, you can oxidize alcohols to carbonyls, right? Whether it just be an aldehyde or a ketone. So that's right, we're going to completely ignore this alcohol whatsoever. So this was a complete the reaction question for you. You're not phased whatsoever. You're going to oxidize that wedged alcohol to a ketone. Remember, we don't have stereochemistry when we have an sp2 carbon, so we are planar, we are flat. We just ignore the OH like an annoying sibling, okay? Awesome. So this was just oxidation at the benzylic position. That's the kind of the concept we were looking at there. Position. Okay, so let's look at the second one. So again, we have this whole structure going on, and we have, yet again, a benzylic position right here. So we have H2 and PDC, or, if it's not PD-C, you'll just see palladium. The fact of the matter is you see palladium, you see H2 gas. This is like, conditions we've been using for a long time, but these are great to do reductions, okay? Whether it's a double bond going to a single bond, or triple bond going to a single bond, we can use H2PDC, and with that special benzylic position, in this case, we have an ether, right? You can see clearly we have an oxygen with an R group and an oxygen with an R group. So what happens at the benzylic position when you have when you have a benzylic carbon and it is part of an ether? When you use H2PDC, you actually do ether cleavage, and it is a reduction, but ether cleavage is probably the more obvious term. So what you do is you actually just sever this bond right here, right down the middle. Get out those molecular scissors, snip. You're good to go. So if you want to be completely thorough, I would draw this as well as this. So the more boring, I think, thing is that you get toluene. Yeah, you do get this benzylic piece, but this is, pretty interesting. And this just turns into an OH. No mechanism needed. You just need to know that you're going to cleave. And just make sure you don't lose any of the stereochemistry, right? We didn't touch that dashed methyl. We didn't touch, the carbonyl. And the OH is still wedged right there. So I feel like these are two things you might run into on a complete the reaction section, as well as this last question. So in this last question, we see we have this benzene derivative. We have a methyl group, and a bromine off of the benzene ring. And we have potassium manganese, right? So what do we got going on? So when you have these alkyl groups right here, potassium manganate, I am so sorry, right? If you have at least one hydrogen available on an alkyl group off of here, right? You need at least one. This will just turn, doesn't matter how long the chain is, doesn't matter at all. It will turn into a carboxylic acid. So you have your benzene ring, bromine is unphased. This turns into carboxylic acid, and this turns into a carboxylic acid. However, if one of these was a T-butyl group right here, right, then nothing would happen. You need at least one hydrogen for this reaction to go. And just ignore everything else, okay? And again, remember, it depends on the carbon directly attached. Okay. So kind of get a little oxidation reduction part of our benzene chemistry, take 2. Okay. So moving right along, just want to do one more quick zone in on the benzene, the benzylic position. So if we look at these two questions right here, and actually I'm going to erase this. This is not that important because I'm going to actually, I realized I should have scratched that out, but I wrapped it into a cooler example down here. Okay, cool. So if we look at this problem right here, we just have toluene to start, right? Benzene with a methyl group. So in this very first step, I'm going to draw my progress up here. We have, that's right, throw back to our very most likely first learned reaction. It's just radical bromination. So remember, you want to brominate where bromine is very selective. You want to brominate on a position that's going to be very stable to hold a radical intermediate. Even though this seemingly looks like a primary carbon, remember, it's going to go through a radical intermediate that's not primary, it's benzylic. And there's so much resonance you can draw right there. So this is good, this is stable. Bromine's very happy to live there. That's the result of step 1. Now, step 2. Clearly we have an alkyl bromide type thing going on. This is just going to prepare to be a Grignard reagent at the benzylic carbon. So the benzylic carbon is going to be nucleophilic. Okay? Now if we look at step 3, all we're doing is attacking CO2. We've done this before. This is actually some carboxylic acid related chemistry. So remember, this carbon commands these electrons. So at 3, we get with a carboxylate, right? We're negative. 4 is just workup. So our final answer is we extend this chain by 1, and we have a carboxylic acid. Okay? Just again, some review that the benzylic position, super stable, right? And can support many charges. You know, whether it be positive, negative, or a radical. Okay? Just don't forget. Easy to forget something so simple, so fundamental. Okay, so what I want to do, actually here, push into kind of phenol country. Give myself some space up top. So remember, phenol is benzene with an OH. So what I want to talk about right now is I want to do an like an acidity ranking question. Okay, so we have these 3 right here. And let's just say each of these, this is structure A, this is structure B, this is structure C. And let's just say from here to here, I want to say this is the strongest acid. And this is the weakest. Okay? So how can we evaluate this, right? So easiest way to do this is we have the acid form here. Let's look at each conjugate base. Let's see which one's the most stable. And finding the most stable conjugate base means that's the weakest conjugate base, which means that would correspond to a really strong acid, or the strongest in these sequence of 3 acids right here. So what I want to do is, since they only vary at the group that's para to the OH, what I'm going to do is I'm going to draw some resonance down here as if phenol just got deprotonated, right? So it would look like this. And then I can kind of just do some analysis on each one, since we only vary at this position right here. So what I can do is I can swing these down, And then I have to bounce these up as a lone pair, right? Carbonyl, lone pair, here and here. Play ring around the rosy, form a double bond, kick these up. Lone pair, double bond, and one more time. Double bond, here, lone pair, and double bond. Okay, cool. So you can see, right, just like as we, if you remember from the fact that this would be an electron donating group, an ortho para director, of course we have a negative charge here, 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 here. So on the ortho and para positions. The question is, how does this group affect the charge's stability when it's down here? This is kind of what we're zoning in on. This resonance structure right here, right? Okay? So if you think about it, what I can do is, what happens, since this is going to be delta minus at this position, delta minus, the analysis we can do is, okay, let's look at the neighboring atom. Here we just have a carbon, right? No big deal. If anything's going on, there might just be slight electron density being put into the ring by the slightest amount by hyperconjugation, so no big deal. If we look here, this negative charge, that will be caused by, these structures acting as an acid. There will be a negative charge at this position, and that's right next door to an electronegative oxygen with lone pairs. If anything, there's going to be repulsion here, right? This charge is not going to be happy when it gets to the pair position and is, running or being very close to the lone pairs on that oxygen in the methoxy group. So I think this conjugate base would be less stable than this right off the bat. So I think B is already worse than A as far as conjugate base stability, which means this would be a weaker acid than A. Now if you look here, I think we're looking pretty prime. When there's a lone pair here, we are next door to a partial positive carbonyl carbon, right? Because it's double bonded to oxygen. So this charge in the resonance will be super comfortable when it gets close to this ester group. So I think this will be the strongest acid because the conjugate base will be the most stable here. So C is the strongest acid. And then as we discussed, it's not that A is touting any great stability, it's more that B is a situation that causes instability. So I'm going to say B is the weakest conjugate, it's not a stable conjugate base, which means it comes from a weaker acid. And then A by default is in the middle, so we spell out the wonderful word cab. So I think this is a good question that you could potentially run into on a final or an exam where you'd have to do phenol acid stability, and the acidity is going to be changed by the fact you're going to stick groups on, right? Okay, cool. Cool. Humming right along. Okay, and real quick, just to round out. Does this round? No, okay. Real quick, just want to say another acidity question. If I had to highlight this hydrogen, this hydrogen, or this hydrogen, which one would be the most acidic? A, B, or C? A is an aryl hydrogen. B is a benzylic hydrogen. And C is just a regular secondary hydrogen, right? You want to go with the hydrogen that's going to be the most stable one, where the charge is the most stable after this H plus is picked off. Aryl hydrogens are not very acidic because you're going to be putting electrons onto a carbon that is in a delocalized pi system. There's going to be some repulsion there that is not great. This is just a regular old H, and we know that carbon just getting a producing a carbanion is very unstable. Obviously, I'm pretty sure this is an easier question. The benzylic position offers the most because when you deprotonate this, you can very easily put this in the benzene ring and go all the way around. So B would be your answer there, the most acidic, because it produces the most stable charge. Obviously, because there's resonance everywhere. Okay, so what I want to do then is I want to run into ipso substitution country. Okay, so first question is I'm going to give you two reactions and we're going to see why one is better than the other. So this would be one reaction. This would be the second reaction. This would be that product. So this question would phrase the following. We call this reaction A and reaction B. Basically, this would say that reaction A is a no-go when attempted in the lab. Reaction B works like a charm. The answer, it would basically ask you, why is this the case? And remember, ipso substitutions work as follows. And remember, ipso, whoa, that's not an X, that's a NaOH. Okay, so remember, with ipso substitutions, the way they work, our nucleophile here is obviously hydroxide. In both scenarios, the way it will work is we would attack this position and then we bounce electrons up there, right? So in both scenarios, we do this. So the fact of the matter is that the relationship between these two right here, this is a meta relationship. Down here, this is a para relationship. If you haven't checked out the ipso substitution video on Ochem, I highly recommend that you do. We have too much to go through for me to draw out all the resonance, but if you look at that video, I explain it in detail. With ipso substitutions, remember, you need at least one electron withdrawing group, ortho, para, or either or, right? To I would say the leaving group, because the leaving group is the site of attack, right? So the resonance will work out stability-wise in this scenario because we are we are para. We have a para situation. Here, in this meta situation, this arrangement of the molecules on the benzene ring will not provide relief and stability for this charge that is created when attacked. So that's why A does not work out and B does, because I would say like B has an EWG para to leaving group / attack site and resonance stabilization is present. That is how, well, I mean, I would draw the resonance, but that is the answer as to why A works and B does not. And like I said, if that's confusing to you, please check out the ipso substitution video on Ochem. I'll make sure it's linked in this video description body, okay? Cool. And I know I'm erasing things right after I do them, but I figure you can, after the fact when this video is available, go back and pause at your leisure. I just want to make sure we fit this in a reasonable time frame, because I always seem to go over the 90 minutes I give myself. Okay, so another kind of, this reaction occurred and we see the following results. Explain why that happens. Okay, and I will draw the mechanism on this one. Okay, so if we look at something like this, So this is going to be nucleophilic attack on a simple haloarene. Okay, so the way this question goes, so given this reaction right here, we have a bromine group right here. We're going to throw in some potassium, some KNH2, and obviously we have NH3 present as well. And we see that we have two products, one of which is the major and one of which is the minor. And what we need to figure out is, why is this the major product? Now remember, this is this is not your typical ipso substitution, reaction flow. Because remember, with ipso substitutions, we have electron withdrawing groups helping to stabilize charges that are created when we put something on the ring. In this scenario, right, we are attacking a haloarene. Haloarene meaning, we have a halogen, we have a benzene ring, we're going to attack an aryl carbon, and there's no electron withdrawing groups. We even have an electron donating group, right? And that's obviously, I think, going to play a role into why we see a major and a minor product. But NH2 minus, basic enough, it's nucleophilic enough to get the job done. So what's going to happen is, and this is in a Ochem video as well, it's the nucleophilic attack of haloarenes video. What's going to happen is NH2 minus, super basic. What it will do first and foremost is next door to where the leaving group is, it is going to deprotonate. Since it's basic enough to do this, it will deprotonate. It's going to grab an aryl hydrogen, an aryl proton, and dump electrons onto the benzene ring. Okay? So the very first thing that's going to happen, nothing going on with the methoxy group, nothing going on with bromine, nothing going on with any of these bonds in the benzene ring, and we have a lone pair right there. So what's going to happen next, right, is that these are going to swing down and form a benzyne intermediate, right? We're forming a triple bond in the ring. We're doing that very strange thing, right? We are going to create a lot of ring strain, we know that, but this happens to then eject the good leaving group, to eject bromine. So we have our triple bond in the ring, we have our methoxy group right here, right? And so the thing is, in that attack of simple haloarenes video on Ochem, we explained that, when you do attack like this with NH2 minus on a benzyne intermediate, there should be, and there is, when you have no substituents, no preference to attack this carbon versus this carbon, right? Absolutely none whatsoever. Hold on, I'm thinking. Oh, yes, okay, got a little confused. Okay, so there's absolutely no, sorry gang, psyched myself out a little bit. There's no difference if you attack here versus here, okay? But obviously this methoxy group plays a role into why we see preference to attack at this position, which is right here, versus this position, which is right there. And think about it, right? Should we attack at either, gonna clean this up real quick. I'm just gonna draw the results of the attack. We either make, remember we'll have a double bond here as a result. We either make this straight away, or we make this straight away. That's a funky nitrogen. So let's look at these negative charges. This one's kind of on its own, right? Just doing its own thing, nothing notable in its surroundings. But if we look at this structure right here, right, this carbon is negative. Well, let's look at its neighbor, and we see that it's attached to a very electronegative oxygen. It itself is partially positive, so there's an electrostatic stability there. There's a stabilizing force. This lone pair will be stabilized by its partially positive next door neighbor. So this intermediate is preferred. It's a little bit more stable. So as a result, to get from here to here, we attack at this position and bounce electrons up there, okay? So in this last step, right, we can just grab a proton from somewhere, probably ammonia. Could be water, could be whatever, what's available. And that's why the major product is where we have a meta relationship between these two and not the ortho, okay? Cool. Okay, I want to round out this with a synthesis question. And then I really need to keep moving because I could talk about any of these individual things all day. Okay, so real quick, given just toluene and Cn-, we have to make this structure over here. Whoop. Okay. So, if you take a look, I think you can see we have the benzene ring. That's what's represented here. We're just counting our carbons. We have Cn-, and I hope you can see we have a carbon and a nitrogen. So I'm pretty sure that's where the cyanide is represented in our product. And I think it's no stretch of the imagination to see this methyl group just being oxidized up there, right? Okay. So what I think maybe was a last step was maybe that if we take this back one step, if we were to use H2 and PD or PDC, that could take us, that wouldn't do anything to this carboxylic acid up top. That wouldn't do anything to this chlorine, but what that would do is, from here to here using H2PDC, that is what could take our nitrile, from being a nitrile, reduced down to an NH2, right? Because this is carbon triple bonded to something more electronegative to it, and we go to something where carbon's only single bonded to it, so that is a reduction. That makes sense, okay? So then if we were to go back a step, now that we've done that, what I think makes sense is that at this point in time, right, if I were to maybe see if I could get my methyl group back, maybe that is something that makes sense that I could do, because I think I could accomplish this with KMNO4, right, with my potassium manganate, right? And remember, the prerequisite for that is you need at least one hydrogen on an alkyl group, right, on a carbon attached to the benzene ring for it to oxidize to a carboxylic acid, but we don't want it to over-oxidize anything else. Well, at this point, our cyanide, this carbon doesn't have any hydrogens on it, so it works out that if we then toss in our KMNO4, we only would oxidize the methyl group here to a carboxylic acid. So we are making some progress. Now we've gotten to a point where we've kind of deduced this back to a point where now we're just trying to figure out how to stick things on this benzene ring here to finish off the synthesis. So what I think is not too hard to see is in this molecule right here, at this point, we have, this, obviously the methyl group comes straight off the shelf. We have the cyanide para, and we have this chlorine ortho. Now this is an electron withdrawing group. This is not what is calling the shots as far as directing. It's this methyl group, which is not a strong directing group, but it is a slight electron donating group as a result. So this is going to direct ortho para. This will also direct meta. And you can see that the chlorine, 1, 2, 3, and 1, 2, if we step this back with some Cl2 and AlCl3, that is the position we would chlorinate at. They both line up. Okay? So now we just need to figure out how, in tarnation, we are going to get this Cn- onto our benzene ring. Now, one thing we have not covered yet, right, is diazotization and arena diazonium ions, right? So we need to reliably put this on. So what I think we can do is use diazotization to do that. So what I'm going to do is just move this farther down here. Again, I can't go through the whole thing, but I would highly recommend watching that series, or that video on Ochem. So what we can do here is if we do Fe, Br3, and Br2, I'm going to start from the beginning. We will absolutely get an overwhelming para-bromination right there. Then what we can do is if we use our sodium nitrite and some acidic conditions, right? That is how we're going to get the, arena, we'll do diazotization. Which so if we then do some heat, right? Heat will make this leave and we'll get a positive charge on this carbon. Then, and I can just do heat and the Cn minus. Once that leaves and that we have a carbocation, I can draw this over here. That's how we get our attack there, and we stick that on. Okay? So I like the synthesis because it involves some of the old benzene chemistry, it involves a whole bunch of the new benzene chemistry, and puts it all together very nicely. Okay? So, again, I know I'm going fast, but we got 3 more sections to go through. So benzene chemistry, in the books. Okay, let's keep going. So I'm going to organize my papers quickly. All right, so let's get hot and heavy with carbohydrates. So very quickly what I want to do is I remember my Ochem II professor, Dr. Nelson, always said every semester when you would do carbohydrates again, some people always ask him, do you always just find yourself memorizing the carbohydrates? And he always said eventually because he would use a bunch of them so much. But one thing he always did, which I find myself doing, and remember, this is a Fisher projection of a sugar because you have an aldehyde up top and an alcohol at the bottom, right? Like the CH2OH, is that he would always just memorize D-glucose. And it helped him then remember everything else from there. So D-glucose looks like this. I always remember you go right, left, right, right. I want to use D-glucose just to make sure and establish the terminology. So remember, so D-glucose. So this is an aldose. An aldose because the carbonyl is an aldehyde. You could have a ketose, and a ketose would look like this. One, two, three, four, five. Yeah, I think I did this right. I don't know which one I'm drawing, but I'm drawing one nonetheless. But you have the carbonyl in the middle of the chain, okay? So you see the ketose, right? That's this right here because the carbonyl is in the middle of the chain because we have this CH2OH up top. And an aldose is when you have your carbonyl at the end, so it's an aldehyde. I think that makes sense. OSE meaning you have a sugar, okay? Glucose, aldose, ketose. So one thing is that when the alcohol from the farthest away from your carbonyl, so here that's this aldose, it's this OH, over here in this ketose, it's this. This means whatever sugar name, whether it's glucose, galactose, whatever, this is a D sugar because it's I always think D, right, dextrorotatory. When it's on the, so that means we have D-glucose. Not only that, so like maybe just as an example, I want to draw L-glucose. So to do that, I have to get the enantiomer of this. L-glucose is the opposite of everything. So it'd be over here, over here, over here, over here, fill in my H's. So in terms of glucose, you can see this is the OH I'm going to consider. This is L-glucose, and they would be enantiomers. So if anyone ever gives you or asks you for, there's no reason to memorize all the D and L sugars. You can just memorize all the D sugars, and then by default, you know all the L's because you can just draw the D and then look at the L's, okay? Now, one more thing I want to explain. This is in a Ochem video, but I want to explain it. If, for example, I took D-glucose, let's just say I switched one of these, like let's just say I took the OH and I put it on the other side. One, two, three, four. Okay. So I have the OH here, but then I have an OH here, and then an OH here, and then an OH here. Okay? If you have two sugars, you need a pair to do this, and they only differ by one stereocenter, these are epimers. Okay? They only differ, so the epimers are diastereomers. Okay? Important terminology. So D and L are like, they are mirror images. They are enantiomers. Epimers vary by one stereocenter, and it doesn't matter which one it is. So here it happened to be this one. Okay? Doesn't matter. And maybe the last thing I want to talk about is if you have a Fisher projection that follows this convention where you have the aldehyde up top and this at the bottom, you don't even have to do stereochemistry, your RNS configuration, analysis. You just go with whatever side the OH is on. So this D-glucose is R, more specifically, we're talking about this is R, S, R, and R. It just matters what side of the Fisher projection the OH is on. If you're in this conformation, okay? So this would be R, 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 okay? And maybe one more thing I didn't mention yet is, since this is 6 carbons right here, this is an aldose, but you could technically say this is in the hexose family, hex meaning 6. If the chain had 5 carbons, you could say it was a pentose, or a tetrose, or a triose, okay? I just wanted, let me make sure. Okay, yeah, that is all the terminology I wanted to go over. I would highly recommend you memorize all of there's only one, triose, but memorize the tetroses, the pentoses, the hexoses. I know it's annoying, but memorize the Fisher projections, and then you can get to anything else, like a Haworth or a chair that you need, okay? So I like this question that I got from Zach Miller, the boy, the legend, the one and only. So on a question he sent me, there was this Haworth, I didn't draw this very well. There's a Haworth projection. Remember, a Haworth projection is when a straight chain loops in to be a ring, but we're kind of looking at it like this. You can do a little bit better than this. There we go. Okay, cool. So we got, so there's a structure given, and then there's questions about the structure. And I think it really puts you to the test as far as what you know about carbohydrates. So I hope this position I dotted right here is the anomeric position, because you can see we have this position right here. There's an OH, and this oxygen is directly attached to it. So this was the carbonyl-carbon that was attacked, and the hemiacetal was formed there, okay? So the very first thing I like to do, or actually there's 4 questions. Let me write these out. Roman numerals. Little circle action, which is nice. Wow, that's a P. And last one. Okay, so let's see if we can answer these without redrawing this, okay? So the very first thing I like to do actually is I'm just gonna redraw this very quickly. And I am just going to, I'm not going to draw the hydrogens per se, but I just like to represent, I like to draw the CH2OH because I feel like that just means, it makes a little more sense to me. So this is what we got. So the very first question is aldose or ketose. Now, like we said, this is the anomeric carbon, so clearly we attacked at this position. So because we have a carbon up here, because it's wedged in between a carbon chain here and this carbon up here, this is definitely this came from a ketose, right, in the Fischer projection. Because it probably looked something like this. Stuff, 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 CH2OH. 1, 2, 3, 4, 5, 6 carbons, yep. And yeah, so if we look at this next question, trios, tetros, pentos, or hexos, let's count the carbons in the structure. 1, 2, 3, 4, 5, and 6. We have a hexos on our hands, even though it's a 5-membered ring. Okay, now furanos or pyranos. Again, so didn't explicitly say this, but this means 5-membered ring or 6-membered ring with an oxygen. And in this scenario, it is a furanos. We'll see more of that when we do heterocycles. Okay, now we need to do D or L. This is where we need the Fischer projection, okay? Because we need to know if the OH here is on this side being D or this side being L. So, what I'm going to do actually is I'm going to erase this. I'm going to show you all how I like to go from a Hallworth projection back to a Fischer. Okay, so okay, so the nice part is that what I like to do is I like to get to a sideways Fischer projection. And when you draw a Fischer projection like this, down here means down, up means up. And you'll see what I mean, okay? So that means basically we are looking at this point, we're looking at this happening. This is gonna come down and reform the carbonyl-carbon, and this goes back. Or maybe I should say, this will grab H+. Basically, I'm just showing the hemiacetal unwrapping, right? Unraveling to be a straight chain. So I need to have 6 carbons. So 1, 2, 3, 4, 5, and 6. So this is going to be my C2OH. Hopefully you can see this. If I do this, I am drawing this carbon and its OH, as well as the double bond here, because we know we have a ketose. Okay? So the next part, so here I can say this is 1, drawing blue, this is 1, this is 2. So 1 and 2. Don't really have to worry about drawing above or below. There. Now, at this position, 3, this is where it starts. The H is up top, and the OH is down below, just like it is in the Hallworth projection. So same with 2, the OH is below, the H is up top, and then down here, H is below, we have a C2, doesn't matter which side, I'm just trying to save space. A C2OH up top, and then this OH is what's on the end of the chain. Okay? So then what I like to do is I like to take my sideways Fischer projection and stand it up. So really we just made this into a straight chain, and now I'm going to just up top, sound effects are necessary. So if I do, here I'll move it down here actually. So if I do CH2OH, this will be my carbonyl. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh yeah, that'll work. Right, we just have 3 right there, perfect. Okay, so I have so if I stand this up, this is on my right, this is on my left. So the OH is here. Then I have another OH on this side. And then I round it out by having an H and a CH2OH. But remember, this is not in the conformation we're used to with sugars, right? With our Fischer projections. If you look at the Ochem video on switching back and forth between Hallworth and Fischer, I want this down here. So to keep my stereochemistry, I need to do a double switch. I need to switch here first. Then once I've swapped those two, I can swap this and this because I want to get the OH up on the left or right side of the skeleton. So the very first switch, what I'm going to do is use the space up here, CH2OH. So I'll do this. This is just my first switch though. I need to do it twice because only switching once inverts my stereochemistry. I don't want that. So then I can do second, CH2OH. I know it's a lot of work for one question, but so I can do OH, H. Okay, so at this point, I have regained this structure at this position, has the same stereochemistry down here, and you can see that my OH is on the right side, and confidently we can box D. So I like this question because it involves a lot of knowledge, right? Basically, can you identify an aldose or a ketose from a cyclical sugar, in its cyclic conformation? Can you figure out how many carbons are involved? Can you, do you know this terminology about oxygen containing rings? And is it D or L? Cool. I'm going to erase this because there's actually one more question. I just couldn't fit it. And the question is, oh, right. So this is the anomeric carbon, right? Let me erase this and erase this. So this is the anomeric carbon. Basically just asks, what is the anomer of this? And that just means we need to switch which way the oxygen went after it got attacked. So the anomer looks like this. And you leave everything else the same. Nothing else changes. It's just the anomeric position, right? Because since when we form the hemiacetal, right when this attack happens, it can happen from above or below, and that depends on, depending on that is where the OH either gets sent up or down. Okay? So this is the anomer right here. Okay? How are we doing on time? Oh boy. Okay, let's do one more problem with carbs. So what I want to do is so if we're given this problem right here, make sure I drew it right. Okay, cool. So, you know what? Okay, cool. So, if we have this right here, what is structure A and B? So, if we look at 1, now think about this, right? This is a throwback to our carbonyl knowledge. We have a carbonyl, and in this first step we have HCN. So the first step, right? We're just gonna do hydrocyan formation. We're going to protonate this carbonyl oxygen, and then CN minus will attack. So the result of step 1 will be this. Didn't touch anything over here. So we have a nitrile, and here's the ticket. This is planar, so when nitrile attacks, it can attack this way or this way. So we get both a wedge, OH, and a dashed OH. Okay? And then in that second step of Dibol, all we're going to do is reduce the nitrile to an aldehyde, right? Because we go through that imine intermediate. So A and B basically we've just produced two new sugars. We started off with a 1, 2, 3, 4, a tetrose, right? Because this is a CH2OH, right? And this is an aldehyde. Now we have a pentose, but not just the one, we have a second, and I hope what you're thinking is, since they only differ at one position, technically, well, not even technically, they just by definition, these two are epimers, okay? Since they only differ at this position, okay? Now some homework for you, since it's going to be some time to do this, right? The second part of the question would be, name these pentoses. What are they? What are these two pentose aldoses, right? And you'd have to do some work to deduce, the Fisher projections. There's a Ochem video on that. I highly recommend that you watch it. I'm going to draw them for you. So this is one. Obviously the other only varies by the one position. Just make sure I don't screw it up though. They're both D. This one is D, which one? Oh, this is D lysose. And then this is D xylose. Sounds similar. They're epimers. I would love it if you could, this is kind of like a little part of your own. You'd have to predict the product here, A and B. Then you'd have to convert them to Fisher projections and come up, the fact you memorize their names, you'd be able to identify them by their Fisher projections. But as a fun fact, they are epimers since they only differ in stereochemistry at one position. They are diastereomers, okay? Okay. Ladies and germs, we are done with carbohydrates. All right. Chugging along. So let's look at heterocycles. Whoop. Let's look at heterocycles. Make sure you know these very, very, very common heterocycles. Remember, they are heterocycles because we have greater than or equal to 2 atoms in our ring. This is the wonderful furan, the wonderful pyrrole, and the one thing I always get the name wrong, thiophene. Okay? All right, so things to note about these three, they're important. They are heterocyclopentadienes. And I think the name actually explains itself as you go through. Heterocycle, 5 things, and there's 2 double bonds, okay? They are aromatic. So they abide by the 4n plus 2. And it is important to know that even though they do not appear so, these atoms up top, the heteroatoms themselves, are sp2 hybridized. They look sp3, but they are sp2, okay? They have a p orbital, right? So they appear sp3, but don't worry, they are sp2 because of the fact that this is a delocalized pi system. So we don't always look like this all the time, right? We are a mixture of the resonance forms. Okay? There are heterocycle videos on Ochem now. The whole series is almost done, with the exception of maybe 1 or 2. Okay? So one of the videos that is currently up right now is the Paul-Knorr synthesis, which I misspelled the name in the video on the whiteboard, which I apologize about. But what I want to do is just some examples. Hold on. Okay, cool. If you just saw me count, I hope you know why I was counting, because I was a little mixed up with what I was doing. And one more. So 3 examples. We're going to do one for each. One for nitrogen, one for sulfur, and one for Oxygen? Yeah, I forget which one I said. Okay, so let's take this one at a time. So let's go up here with sulfur. So remember, with the Pal-Nor synthesis, which I'm going to spell correctly up here, P-A-A-L, Nor. Okay? Remember, you need a gamma dicarbonyl. That is the requirement. And this helps us make thiophene derivatives, pearl derivatives, and furan derivatives. So remember, alpha, so from the carbonyl, alpha, beta, gamma. Cool. So remember, now that we have, you've established we have an alpha beta dicarbonyl, I like to, since I know I'm working with sulfur, I will have this shape. Jeez, oh man. Okay, cool. This is alpha, beta, and gamma. So I know that these right here are just my R groups, and they are both the same. We have symmetry. They're ethyl groups. There we go. I've predicted the product. Super, super simple. Okay, let's look at this right here. So we are making a furan derivative, right? Because we have diphosphorus pentoxide. Okay, nope, don't count like that. Alpha, beta, gamma. Alpha, beta, gamma. Cool. So what I'm going to do is I'm going to draw my cyclohexane ring. And I know, so you can kind of see that it's this carbon, this 1, 2, 3, 4, and then oxygen kind of will go here for 5. So I'm going to make my ring like this. Double bonds here, oxygen there. There's my furan. I just need to bring these phenol groups along for the ride. Don't even need to draw them out. Bam. Easy. Last one. Let's look at this. Let's make a pearl derivative. Alpha, beta, gamma. Sweet. Let me just nitrogen. Bring along the nitrogen's R group for the ride. Happens to be an isopropyl group. And I don't have symmetry here, so on one, I have a methyl group, right? Remember here and here. And then over here, I actually have an isobutyl group. Get a little blast from the common naming past. Okay, these are something I would highly expect for you to see on a complete the reaction question. Mechanism, I'm not quite sure, but the mechanism is on Ochem, so if you do need to know it, check it out. Okay, humming right along. Heterocycles, no big deal, am I right? Okay. All right. Oh, another Pal-Nor synthesis I really, really, really like. This is from the textbook, which I thought was a great question. Okay, cool. So there's 2 steps here. So clearly we know that, remember, for Pal-Nor synthesis, we need a gamma dicarbonyl. We do not have that given to us, but I imagine in the second step, right? The second step, don't know what the first step was. Second step, we must have had, I want to draw that dicarbonyl. Must have looked like this. Ethyl. Okay, because alpha, beta, gamma, right? Alpha, beta, gamma. That would put the ethyl there. And then off of the, we have this carbonyl right next door to the carboxylic acid. So, and we just see NH, so clearly this is just our ammonia, and we just need some acid. Okay? So, what gives? What did we do? Well, we have a 4-membered ring here, so how do we split that open to get here? And not only that, but how do we get carbonyls on what seem to be the carbons involved in the double bond. Well, I hope this is ringing a bell. We need to reach back into the Ochem I vault and do ozonolysis with zinc, because what that will do is that will give us aldehydes on terminal carbons, part of a double bond, and, you know, as well as just a carbonyl in general. That is what gives us this. It opens up the ring to then allow us to do the polymer synthesis. I thought that was really cool. Ozonolysis seems to be that thing that always pops up, but I think it's because it helps you disguise a problem so well by giving someone a ring that they have to open up. Thought that was a cool example. Wanted to toss it in the review. All right, we are humming along, gang. Hope you're having fun, because I'm having a blast. Okay, so just remember, when you're doing EAS with heterocyclopentadienes, remember, if you don't know this for sure, we do EAS at C2, not C3. By that, I mean you always give, when you number, you give the heteroatom, the priority number 1, and then you go around the ring. You do branching, you give the lowest numbers to where there's branching. So this is C2, C3, C4, and C5. Or for example, so there's no C1. Or for example, let's just say we put a chlorine, chlorine here. This would be C2, C3, C4, C5, because we want to give the chlorine the lowest, number per se around the ring. But because of how the resonance works out, we say, for example, we just do Cl2, you do EAS at these positions first, okay? So we have chlorine right here, and that is how that goes down. And if you want to see how the resonance works out, check out the Ochem video, uploaded today, okay? Cool. Again, going fast because I want to make sure, we have 22 minutes, I want to get through the rest. Okay, so I was going to do a Hansch pyridine synthesis question, but I am uploading that video right now to Ochem. It's a bit long, but it goes through the mechanism, and at the very end we do 2 complete the reaction questions, and you will see how easy that concept and problem is. So I would say for the Hansch pyridine synthesis, check out the Ochem video. Pretty sure it should be ochem.io videos. It's in the Heterocycles, but if you wanted to go directly to it, it would be at that URL. It was uploading when I started this live review. I don't know if it's done. It should be soon though, okay? So we will not do that. So what I want to look at is some acid-base stuff with heterocycles, because I think this can be very tricky sometimes. Yes. Okay. So let's take a look at this. I want to give this the time it deserves. So Hansch pyridine synthesis was going to kind of be our introduction to pyridine, but we can do that right now. This is pyridine, right? It's a heterocycle because nitrogen is embedded in the ring, and it is aromatic. So if we were to look at this, don't be tripped up though. I know we're so used to saying, oh, we got to include electrons in the ring to make it aromatic, right? In the case of pyrrole, for example, right? This is pyrrole. Okay. However, nitrogen is straight up a part of a double bond here, right? So it brings an sp2 orbital into that pi bond. So in pyridine, the lone pair actually, because remember, to be aromatic, we need 4n plus 2 for Huckel's rule. That needs to check out, right? Clearly we have 2, 4, 6 pi electrons just from the double bonds themselves, right? So we don't need nitrogen to donate these electrons to the cause. If anything, that ruins us and takes us from 4n plus 2 to 4n, which we know is bad news, right? So nitrogen being sp2 hybridized just sticks the electrons in a perpendicular sp2 orbital. Just some background. Okay? The question here is, this is A, and this is B, and this is C. Who is the strongest base? Who is the weakest base? And I feel like this question sometimes throws students off because they're so used to answering strongest acid, weakest acid, right? The thing is here is that also there's some extra things at work, and that's why I want to give this question the respect it deserves. I think I just spelled pyridine wrong. Incorrectly, rather, pyridine. Okay, cool. Oh, maybe I had it and then I misspelled it. Okay, cool. So, and then this is, oh, I have the name misspelled, I think. I can't read it. Okay, so A, B, or C, strongest to weakest. So, here's the thing. I want to talk about pyrrole first, and then pyridine, and then this. So this is your run-of-the-mill amine, right? The pKa here, roughly 35. Man's is a pretty strong base. pKa is high, it's not low. So this would be, and it's not very good, right, to weak acid. So it's, by default, a strong base. So if we look at these two, if we look at pyrrole is a very, very, very bad base. Because if this was to act as a base and grab H+, what we get just by doing this, we have lost aromaticity. Okay? So if we looked at an energy diagram, pyrrole being super stable down here, right? Just from undergoing this reaction, because we lose the electron pair, which enables us to have a delocalized system and be aromatic, all this stability, right? We're low energy, right? We're stable. We go from low energy to a much higher energy state, right? And it's probably not the best energy, a little hump right there, whatever. There's probably high activation energy, but this is bad. The conjugate base is not weak. The conjugate base is high energy. It's unstable. So this is a bad base because the conjugate acid is unstable. This would be a great acid. This thing would just give H+ away to anybody. So this is the worst. Okay. Now let's look at pyridine. Now, like we just discussed, this electron pair is not tied to pyridine's aromaticity, right? So it does not have the same problems as pyrrole in that department. It has a slightly different problem, but it's not nearly as bad. The thing is that these, like we said, these electrons here are in an sp2 orbital. Because the orbital has more s character, those electrons live closer to the nucleus. Who lives in the nucleus? Protons. That means those electrons are a little bit more stable than typical electrons, like these ones right here being in an sp3 orbital. So this nitrogen has the nucleus here has a stronger hold on those electrons that are going to be needed to grab H+. So the fact of the matter is that pyridine is not as strong as a base as this generic amine. So we have A being our strongest base. We have C coming in second because we don't have aromaticity disruption, and pyrrole comes in last place in the base department. So ACB. I think this is a really cool, unique acid-base question because it's not just so much like resonance, right? There's aromaticity involved, and that for this, justifying why B is such a bad base, as well as here, it's a hybridization argument, okay? Which is why I like it. All right, gang, that rounds out heterocycles. So we are moving into the home stretch of the review. We are doing DNA, amino acids. Let's get it. Organize some papers, because I think we're doing about 15 minutes, and there's plenty of time to do this. Let me go. Whoops. anyways. All right, so one thing about, so with DNA, we'll do peptides. DNA, well, we'll just do DNA, RNA, whatever. Okay, so I don't have a, some teachers like to teach this, some teachers do not like to teach this. So this is gonna be it's like a light skim of what's to come. So I won't have the videos possibly ready, but I'm sure I have full faith in whatever I may not cover here, you have already covered. So what I do want to talk about is, so there are 20 essential amino acids. When I went through Ochem II for the exam, it wasn't on the final that I had, was kind of tested on them, it was on my third exam. I had those suckers memorized. So know all of those, which is really annoying because you might get hit with carbohydrates and amino acids at the same time and you're like, oh, isn't organic chemistry? Everyone always says don't memorize stuff. And yeah. And maybe you have a professor that, no shade at whoever I had, but maybe you have a professor that just gives you a table of them. But if you need to memorize them, don't think you're like too good to memorize them. Just commit them to memory for the test. If you need them, just please do it. Because you don't want to lose stupid points when you need to. Like, for example, that one question I gave you where we had to name, D-lysose and D-xylose, like that was an actual test question I had where I had to actually come up with those names and it was worth like 5 points. And if that's on a 100-point test, you do not want to lose 5%, right? Exactly. So, commit these to memory, you'll need to know them. And you'll see a question where we will need to know them. So, there's a bunch of different ways to do, I'm just gonna erase this. So when you have amino acids strung together, that's how you can get peptides, right? So when you have just a few amino acids strung together, right, you can have a dipeptide, a tripeptide, a tetrapeptide, or more generally, a polypeptide. And if you have enough if your peptide chain is long enough, you get to a protein, okay? So what I want to talk about is one thing called a Strecker synthesis. This is one method to do peptide synthesis, or amino acid synthesis rather. So the Strecker synthesis goes through an imine formation. So, I should even say generally a amino acid is, I'm not drawing stereochemistry right now, but you have a carboxyl, I did it where we have a Zwitter ion, something that is neutral but it has charges in the structure. You have a carbon right here, and on one side of the carbon you have a carboxylic acid. In this case it's a carboxylate. Then here you have an amine, here it's in an ammonium state, and then you have an R group, and the R groups vary, and that's what you're really going to be memorizing when you memorize amino acids, okay? So if you string a bunch of these together, that's how you get peptides. So the Strecker synthesis is a method to produce the individual amino acid blocks, right? So, for example, if I wanted to produce alanine, an amino acid, which looks like this, the R group is just a methyl group. Via a Strecker synthesis, you can do this. So you start off with the carbonyl and the R group you need. So this carbonyl, this carbon right here, is going to be this carbon in here, and you can see our R group is right there. So we have acetaldehyde to start, and what I can do is if I just toss in NH3 with acidic conditions, I will form an imine right there, nothing new. And then what you can do is, so basically you can see I have this going on, right? Because that carbon is there. I need a carboxylic acid, so you can use cyanic acid to then tack on like this. And then all you need to do is hydrolyze the nitrile to a carboxylic acid, and then depending on whatever pH you're at, you'll have this in a, the charges will be there, but the Strecker synthesis is just about taking what you need it better have a carbonyl, right? In this case, it's just a 2-carbonaldehyde. Take it to an imine. By making the imine, you then introduce the nitrogen part of your amino acid. Then you use hydrocyanic acid, I apologize, hydrocyanic acid to then introduce what will then become your carboxylic acid. You hydrolyze it, that's how you get it. What's important to note is that this produces a racemic mixture. So if you need to, for example, if you have a question that says like, oh, you need only S configuration, which is the configuration most of the essential amino acids take on in nature, then you'd have to separate this. But that's a whole other discussion. Okay? The Strecker synthesis. Okay. So that's how you would make individual amino acids, synthetically. But what I want to talk about is, peptides, stringing amino acids together. So you can have as many as you want in a row. So depends on who you're working with, but for example, peptides have, here, I'm going to draw this out and then I'll speak to it. R2, R1. Okay, so I drew a real simple dipeptide here, but in peptides, you alternate by having, this would be one end, so that's why you have an NH2. This is one end, that's why you have a full-on carboxylic acid. But in between, you have all these, you have your R groups. You can see the presence of individual amino acids because you have this carbon attached to an amine piece, this carbonyl with its R group. When you string them all together, you have a bunch of amides right here. So when you talk about the structure of peptides, remember when we discussed about amides, because of the fact that this resonance is quite a big contributor, right? This double bond is it's in between, its characteristics, in between a single and double. So the thing is, rotation about this bond is hindered. It doesn't really happen. It's very rigid, okay? So that's a very important thing. It's sp2-like, this bond, right? So, if you ever get a question like, why is there rigidity in the backbone of peptides and things like that, it's because of the amide bonds, because they have sp2-like character. And it comes down to the resonance. So if you were to, you can, each amino acid in your chain, you can refer to those as a residue. So, you'd be like, oh, that phenylalanine residue, and things like that, if you want to sound smart. So one thing I want to do real quick is one question that could be, something you could run into is maybe, so people can draw amino acids like this, and they'll use the abbreviations like this, which is really annoying because it's like, not only did you memorize the structure and you memorize the name, but you have to memorize an abbreviation, but you can mostly tell them based on just looking at them. So this is going to be an amino acid with phenylalanine, leucine, and proline, okay? So what the question would look like is draw the structure. And when someone asks you to do this, unless they state otherwise, assume C2, C2 meaning this carbon and this carbon, C2 is S as far as its stereochemistry. So that's right, you won't draw this just straight, just completely flat. You will have to use wedges and dashes when you put on your R groups. So the thing is, to be honest, I do not have these committed to memory right now. So I will go ahead and what I'm going to do, and you can just assume that you should have at what is called, so when you draw an amino acid and you have the ends, for here I'm going to draw like the carboxylate. This would be the C terminus. And then at the other end, we're going to have an NH3+, and this would be the N terminus. Okay? I'm going to go ahead and draw the structure, but I am going to keep everything flatline first, because I know you all can memorize stuff. I know You got big brains. That's no problem for you whatsoever. I am more, once you would string these together, and we can look at this in a second, I would want to make sure you know how to properly ensure that these have the correct stereochemistry. Proline is a weird one because it has its nitrogen embedded in its R group. Oh man, gave it away. Okay, cool. So if we look at this right here, you can see this is phenylalanine right here. So this would be the phenylalanine residue. This would be the leucine residue, and then this is the proline residue, okay? So this is the C terminus, this is the N terminus. So it's these carbons right here that we need to determine the wedge or dash, essentially. So we need to make sure this is S, S, and S. So if we look at this, directly off of this carbon, the heaviest thing is this nitrogen. Then it's going to be the carbon that's double bonded to oxygen, then down here. So if we look and we do our lowest priority group is a hydrogen, right? And since these are two flatline and we're about to decide if this is a wedge or a dash, right? So it looks like S. So we should make this a wedge because that means that the hydrogen is a dash and that S is actually S. This is supposed to be a wedge, okay? So let's look here. Heaviest thing off here is the nitrogen, then it's this, then it's the R group. So it looks like R, but we want S. So since we haven't drawn the hydrogen in, if we make the hydrogen a wedge and we dash this line right here, it looks like R, but it's actually S. Let's do it one more time. So that's good too. Here, nitrogen the heaviest, then over here, then here. So it looks like S, that's what we want. So let's dash this so that the hydrogen is, let's wedge this so the hydrogen is dashed. So you should be able to do this, you should be able to switch back and forth, okay? Cool. So I think that is what you would need to do in peptide land. So annoyingly make sure, just like eating your vegetables, just memorize your essential amino acids, structure and abbreviation and name. Okay, so I assume a lot of you have probably taken biology, but I know we talked about polypeptides, aka proteins, but in protein land, just make sure you know what primary, I use this abbreviation, it's probably not correct. Know what your primary structure is, know what your secondary structure is, tertiary and quaternary. So with your primary structure, right, it's actually like what amino acids are in your protein. In the polypeptide, okay? Know the two types of secondary structure. Know that you can have an alpha helix or beta pleated sheet. Know roughly what that means, right? The beta pleated sheet is looking like this. You have hydrogen bonding going across. And then know that the alpha helix, right, is a helix, and there's hydrogen bonding there as well. Know that your tertiary structure is because it's, R groups interacting across the protein and how it folds, and that things like heating the protein up can potentially destroy tertiary structure because it can denature protein, it can destroy disulfide bridges, all that stuff. And then your quaternary structure is just protein interaction with another protein. Interact with other protein. English is hard sometimes. Okay, so I took biology 1. I took bio 1, so you're probably more well-versed in biology than I am. So just know your different types of structure, maybe just a concept question about like why something happens or doesn't happen based on temperature. You talk about tertiary structure and denaturing of a protein. Not your traditional organic chemistry question, in my opinion. All right, last little tidbit. Give me 5 or 10 more minutes. Real quick, DNA, RNA. Just more terminology than anything. So, a 1 nucleotide that consists of a sugar ring, a nitrogenous base, and a phosphate group, okay? If you were to only have these two things, you could technically say you have one nucleoside, okay? So just know that means no phosphate, you have a sugar and a nitrogenous base. So you have the whole shebang, it's a nucleotide. You have these two out of the three, you have a nucleoside, okay? So annoyingly, you should know the structures of G, C, and T and A, right? So you're gonna need to know them, and obviously uracil, but what I wanna highlight very quickly is this, and it's cool because we know carbohydrate stuff. This is, I'll do CH2OH, 2-deoxyribose. You should know this as well. So this sugar is what is in DNA, okay? Now, if you just have ribose, that is what is in RNA and what is different. So the cool part is that this thing, 2-deoxyribose, means just no, no. So if we number 1, 2, and 3, and 4, that just means there's no OH here. In ribose, that's the only difference. OH, OH, CH2OH. So just memorize ribose, and then you know what 2-deoxyribose is, okay? So this is the sugar that's in RNA, this is the sugar that's in DNA. If we wanted to put a whole thing together, right, one nucleotide, it would look like this. I'll use 2-deoxyribose. You have a phosphate here, and then you could have more. Oh, whoa, sorry. Got all mixed up. So, and then we do base. So if you had this is a nucleotide, right? I used deoxyribose, oh man. There we go. Sorry, gang. Sorry. Right? So if you have this nucleotide, right, you just basically have to attach a phosphate group up here, a nitrogenous base right here, and then you have your sugar. That's all that is different. Okay? Then you have a bunch of them in a row. So you get strands of DNA and strands of RNA. Okay? And last but not least, I just want to mention that you should know that G pairs with C, A pairs with T. This is for DNA. And for RNA, G still pairs with C, but we don't have T available in RNA. We have A pairing with uracil. And what you will need to know, I think, if anything, you would have to know these structures and explain why they pair. And it's because with G and C, you have 3 hydrogen bonds. They get along real well, and those pieces fit together, and that's the maximum, G and C could do together, and that's why they like to pair with each other. And with A and T, you get 2 H bonds. That's the best those pairs can do, and that's why they're with each other. Know these structures, know how to draw the hydrogen bonds they form together. If you want to know what that looks like, just Google it or look in your textbook. All right, gang. Thank you for hanging with me on this Easter Sunday. You're all awesome. If you had any questions, please leave comments on this Facebook, live stream post. As soon as it's done, I'm going to download it. I'm going to upload it to YouTube, and I will make it available on Jochem. I will make a post on the Jochem Instagram. If you don't follow the Jochem Instagram, if you don't like me here on Facebook, give me a like on Facebook. Give me a follow on Instagram at Jochem_IO. Most importantly, if you haven't subscribed on YouTube, please do. Try to get to 1,000 subscribers so I can start to do some mobile live stream, because Facebook live stream is not my favorite, But if I have 1,000 subscribers, I can do it from YouTube and the quality is much better and I'm a happier person and a happy Joe. I mean, I like to be a happy Joe. So help me out. Throw me a subscribe. If you do, I'll love you. And if you don't, that's okay. I'll probably get over it. Thank you for a great semester, Joe Chemists. This has been a dream come true. To think we're so close to even 100,000 views on this project is crazy. That to me, I feel that means people are learning. And that's what this is all about. So stay strong with all the craziness going on. Wash your hands. Stay safe. If you can help someone out, lend a helping hand. And always, I will see you all in the next video.